We're asked to determine when this particle traveling along the x-axis is slowing down or speeding up. We're given a function x of t, which gives us our position. And we know in order to find if a particle is slowing down or speeding up, we need to know its velocity and acceleration. If it's speeding up, its acceleration and velocity will have the same sign. If it's slowing down, the acceleration and velocity will have different signs. So how do we determine that? We got to make a double sign chart. To do that, we need to know our critical points and our candidates for points of inflection. To find all of those things, to find our critical points, that's the first point. To find critical points, we're going to need to find the derivative of the position graph to find velocity. We know that x prime of t is our velocity, and in this case, that's going to be 3t squared minus 30t. And then we also need to find candidates. I'm going to shorten this, candidates for points of inflection. And to do that, we need the second derivative, which we know is the derivative of velocity, which is acceleration. In this case, that's going to be 6t minus 30. I'm getting that from here. So, in order to find critical points, we set this equal to 0. So we get 0 equals 3t squared minus 30t. I know that both of these numbers are divisible by 3, and so I'm going to say 0 equals t, or both these terms, sorry, t squared minus 10t. I'm going to factor out a t from both of these. And I see, based on the zero product property, that t will either equal 0 or t equals 10. Now we need to check for candidates for points of inflection. To do that, we also set the second, now we set the second derivative equal to 0. I'm going to add 30 to both sides, divide by 6, and here I'm going to find that t equals 5. And so we have the points that are going to check all of our intervals. One thing I know is that I want to organize this into my table in the order from least negative to most negative. And so least negative to most negative, that's going to be 0, 5, and 10. Just keeping that in mind as I make my table. There's t. And what we care about are the signs of our velocity and our acceleration. One thing that's important to keep in mind is where the domain is. For a lot of times, we might just write negative infinity to our first value. But here I see that we say t is greater than 0. So we always want to start at 0. 0, comma, and we go to the next value, which is 5. And then from 5 to our next value, which is 10. And then here from 10 to infinity, because it doesn't say anything about when it'll end, it just talks about the stipulations for where it begins. It has to be greater than 0. All right, so we know that the velocity at 0 and at 10 is 0. So we can mark that now. We don't have a place for 0, so we're not going to mark it. And then we also know that the acceleration at t equals 5 is 0, so we can mark that as well. Now, what's happening in these other regions? Well, let's say if we picked 5 as our velocity, let's see, or as the time for our velocity. Let's see what happens. If we plug 5 into this equation, v equals 5 times 5 minus 10. This will be 5 times negative 5. This is going to give us a negative value. And we know that'll be negative 25, but it's just negative. And so that tells us that all of these are going to be negative. That whole region will be negative because there's no place where the velocity is 0 for it to change from negative to positive. All right, what about from 10 to infinity? We can plug in another number here. So let's try plugging in another value for our t that is greater than 10. So I'm just going to plug in 11 here into this. So we're going to get equals 11 times 11 minus 10, which would be 11 times 1. And we know that's 11, but all we care about is that it's positive. It's a positive value. Great. Now we need to do the same thing, but for the acceleration. Here I see I want to find a number between 0 and 5. 2. Cool. We're going to plug it in here, right? I'm going to erase this so we don't get confused by it on this side. We're looking at the green, and so we see, okay, let's plug in 2, 6 times 2, minus 30, 12 minus 30. I don't really care what it is. I know it's going to be negative, though, because we're subtracting a big number from a small number, so that means that anything over here will be negative. Now let's test out on the other side what's going to happen. Well, I'm going to test 10 because I see that that number is there. So 6 times 10 minus 30, 60 minus 30. I know that's 30, but all I care about is that it's positive. And since this is positive, all of these are also going to be positive because we're looking on the other side of our potential point of inflection. All right, the final step is to figure out where are we slowing down and where are we speeding up. How do we do that? Well, we know that we are speeding up. We've already determined that by saying where the velocity and acceleration have the same sign. I see that happens here in this interval, and I also see that happens here in this interval. And so I can name, and I'll write this, particle speeds up on 0 to 5 and 10 to infinity because v of t and a of t have the same sign. It's okay if they're both negative, because what that means is we have a negative velocity, we might be moving to the left, but we're moving to the left faster and faster because of the negative acceleration as well. Now, what about when it's slowing down? We know it's slowing down when they have different signs, and I see that, fudge muffins, I see that happening here. And so we will name that the particle slows down on this interval. It's the only place, 5 to 10, because v of t and a of t have different signs. And there we are. That is how we determine whether or not a particle is slowing down or speeding up.